is now being recorded.
Hello everybody, thank you for joining us today in the third Spring HIS Cyberseminar. My name is Jonathan Pollack. I'm the User Support Specialist here at the CUAHSI office. And today we're going to have three speakers rather than the regular one. We have Matt Over, who's a graduate student working with Yoram Rubin at the University of California at Berkeley. Carlos Osorio, who is a graduate student at Brigham Young University, as well as Professor Dan Ames, who gave last week's cyber seminar about the development of Hydra Desktop. So today we have Matt, Carlos, and Dan who will discuss a method for characterizing uncertainty in model parameters, and this software has actually been developed as a Hydra Desktop plugin. So with that, I'll actually hand it over to Dan, who we left off with last week on Wednesday, who will speak a little bit more about Hydra Desktop and about, this example of one way that the software is extensible. So Dan, please take it away.
Thank you, John. Hello, everybody, and appreciate you joining us today for this call, and also those of you who might be watching later on YouTube. This presentation is about the method of anchor distributions, which is a technique for doing inverse modeling that we've constructed into a framework for model inversion, as you can see on the slide here. What we'll do in our presentation today is start with a brief project introduction and goals that I will give. Then I'm going to turn it over to Matt Over, who will give you a little bit more background on the method of anchor distributions for inverse modeling. And then we'll turn it over to Matt and Carlos Osorio, who will do a live demo of the MAD-Sharp application as it stands now as a application that lives in close connection with Hydra Desktop, the plugin, and also a standalone application. And then I'll just give a couple of summary remarks about where the project's going. So this presentation will be largely of interest to people who are involved in or interested in inverse modeling. And just a quick summary slide here of what is inverse modeling and what is the problem we're trying to address in our NSF-funded project. The inverse problem is essentially to try to estimate variables that can't be directly observed using observable data. For example, given observed gravity, what's Earth's density? Or in the hydrology area, oftentimes we have given observed characteristics or measurements of groundwater and groundwater movement, what is the distribution of the subsurface parameter of interest that's driving that movement? So this is an important and also complex problem in hydrology. It's been around for a number of years. People have been working on it for a number of years, but it's extremely difficult for every new researcher to learn from scratch. It requires a wide range of knowledge, statistics, hydrology, spatial analysis, and so because of this, and also a strong background and understanding of uncertainty quantification. And because of these needs, it has had a sort of relatively slow adoption in decision-making areas while it's advancing quite quickly in the sciences. So our goal was to develop an open framework, a software framework that could be used to do inverse modeling, to help with adoption of the technique, specifically the MAD technique and also inverse modeling in general. And we'd like to see, we recognize that this kind of approach of building an open framework has happened elsewhere. Obviously, the HIS is a really good example of putting out standards and tools and APIs and letting people program against them to add on and build new tools. And we've tried to follow the same approach. Hopefully, as my bottom bullet says there, as we do this, inverse modeling can be picked up and used more readily in education and training environments. So our overall goal, and these are some of the requirements that came out of our proposal to the National Science Foundation, was to make advanced inverse modeling techniques more accessible, to use a very open software design and development approach that could encourage other individuals and groups to join in an effort, and that includes being very modular, so that as we found with the CUAHSI HIS project, the more modular you are, the more easy it is for other individuals and groups to write tools and plugins that can work with your software. So we're following this kind of approach with the current project, MAD, and ultimately to allow extensibility so that other individuals can add new capabilities. In particular, our framework is set up so that you can plug in new models. And so rather than sort of having an uncertainty characterization technique that is encoded into or built tightly integrated with an existing model, we've built more of an uncertainty quantification framework for inverse modeling that models, the other models, models like groundwater models, surface water models, or any kind of model for that matter, could plug into. So at this point, I'm going to turn the microphone over to Matt Over, graduate student of Dr. Yoram Rubin at UC Berkeley, who can give us a bit of background on this technique, the method of anchor distribution.
Thank you, Dan. Hello, everyone. So I just want to give kind of a brief overview to provide some context for the demonstration we're going to see later in the presentation, so that the software kind of has, we get the feel for what we're trying to do with the software. So I like to give a couple selling points for what MAD is, the method of anchor distributions is MAD. First of all, it's a general Bayesian framework. Like Dr. Ames said, it can be extended and applied in a variety of situations for conditional characterization of parametric uncertainty. And I'll develop what that means in greater detail as we proceed through the presentation. The nice thing about it is you maybe have heard of calibration or optimization schemes. These yield an estimate or a single best value for a parameter. Our goal is not to obtain a single best value, but an entire PDF, a probability distribution function for the parameters instead of a single estimate. So we have better kind of information about the uncertainty. And finally, MAD, because it's a generic framework, allows us to condition on multiple types of data jointly and to get our parameters conditional on different types and scales of data in the same kind of synthesis and investigation. So, being a Bayesian philosophy, we work off of this governing proportionality, which is very similar. It's just there's one constant missing from Bayes' rule, which is a classic equation most of us should be familiar with. The idea here is that we want to obtain parameters that are conditional on data. And this is our posterior distribution. And to do that, what we need to do is we need to define a prior distribution of the parameters, and then we condition using the likelihood. So we get the data, the probability of observing the data given the parameters. And this is the big goal of MAD, is to solve this likelihood function. So our objective, we obtain this distribution of parameters conditional on the data that we have that's relevant at the site. And the way we do it is we solve the right-hand side of the equation. So I want to give a brief overview of what I'm going to cover. I have about 10 slides today. First, I want to describe the parameter space and the data space. They're quite essential to understanding what's being applied in MAD. Then I want to briefly introduce the Monte Carlo procedure for the likelihood inference, because the MAD software will automate this process, and so I'd like you guys to see a little bit what the software is doing in the background. And then let's see it in action. So I have to introduce a couple terms here to frame out my discussion. First, I said I would talk about the parameter space. This is divided into something called anchor parameters and structural model parameters. Now this is just a categorization scheme that I'll explain in greater detail as we go. And then we have the data space is also categorized into type A and type B data, and I'll define these also. So I like to give a couple little graphics here. The parameters are kind of the controls of the model and the controls of the physics, and then the data is what we can observe and collect and what we get from all these data loggers and this mass proliferation of data being acquired. So what's the role of the parameters? The parameters here are used to describe our target variable field. And so let me give a couple examples here. Here's a random field, and maybe in hydrology we're a little bit more comfortable with the idea of a transmissivity field or a porosity field or a permeability field. And all these could be a target variable. Essentially the target variable is what you would like to describe or characterize through the MAD inversion. But why is it called MAD? This is an important aspect. It's called the method of anchor distributions because of what an anchor is. Now, an anchor is actually a probability distribution of the target variable at specific locations in the field. So synthetically here we can put a couple anchors represented by these red dots, and we can determine distributions of the target variable y, or in this case represented by alpha, at those specific points. Now the important thing about anchors that's often confusing is that they're not actually measurement devices. They're purely statistical. So you can place them mathematically and statistically wherever you like at your choice in the domain. And so people start thinking, well, if I can characterize the distribution of a variable at one location in the domain, why don't I just cover my entire grid mesh? And that's because there's a high cost affiliated with a lot of anchors. Every anchor would count as a parameter, a dimension in the parameter space, and the cost of our Monte Carlo investigation grows nonlinear with dimensionality. So that's one problem, is just cost limitations. And the other kind of motivation is that if you have scarce data, which is often the case in subsurface applications, you have limited amounts of measurement wells and a large spatial domain you're trying to characterize, you can have mathematical challenges from ill-posedness or underdetermined problems, meaning you have not enough data to determine the number of anchors uniquely. So short end of the story there is the dimensionality of our investigation leads to high cost. So we want to try to mitigate cost. So if we can't place an anchor everywhere, how do we actually represent that entire random field that I showed before? We need something that fills in the gaps, so to speak. So this is what happens and why we have that second category in the parameter space called structural models or structural model parameters. Now these are random structural statistical models, and what I want to do is kind of walk through a simple example here. We have here a simple grid. I have some anchors, so these are locations where I'm going to have distributions of the target variable directly, but I need the entire field to simulate my data. So the structural model, S of the target variable field, given the parameters, fills in the remaining gaps of the field to give us a complete picture of perhaps the permeability field or conductivity field in the domain. So to summarize the parameter space, we have anchors that describe the uncertainty at specific locations, but not the whole field. We have the structural model to fill in the entire gap so that when we generate random fields, they give information of the parameters and the target variable everywhere. But here's the spoiler. We have to have some compatibility. If we're going to fill in the gaps, we need to make sure that the gaps don't overwrite the point-specific data. So this is classically geostatistical conditioning, meaning that the anchor values are reproduced by the structural model and not overwritten or overridden. So the parameter space is admittedly more confusing. The data is a lot simpler. Type A is directly related to the target variable field. And so this means we can measure it and it immediately gives us the value of the target variable somewhere in the domain, or we can apply some kind of simple regression to obtain a value. Type A is commonly the inputs to forward models, and by forward models I mean something that numerically solves the physical governing equations. And again, they must be compatible with the structural model. The structural model can't override this information. I have a straight ahead arrow here just to kind of give the idea that type A is very easy to incorporate. It's a direct route. Type B is now indirectly related to Y, and this is an interesting thing. Type B is what allows us to calculate the likelihood function. It's the reason we use a forward model, and these are any kind of information that can be indirectly related to the target variable. So a simple example, hydraulic head is not related directly to one hydraulic conductivity. It's actually a volumetric representation based on boundary conditions, initial conditions, and forcing conditions. But through the flow equation, or some kind of ordinary differential or PDE, we can get some information about the target variable conductivity via the head measurements. Now, the type B, maybe more simply, can be thought of as the output of a forward model. So we have data that goes in, and we have data that comes out. Now, a little reminder, this is harder to get to, so it has a detour sign. So we expand the formula now with for Bayesian proportionality, now with the qualified terminology. We have, again, the posterior, the likelihood, and the prior. The data, you'll recall, was ZA and ZB. The parameter space is structural parameters and anchors. And our goal here is to first specify a prior based on some other sites or some kind of reasonable, least subjective approach. We infer the likelihood function by collecting measurements of ZB and performing a Monte Carlo analysis. And this is performed with the MAD software. Out of the output, we obtain the posterior distribution of the structural parameters and the anchors, conditional on both types of data, and that's the important part. So, a little bit about the Monte Carlo process. We see in the likelihood function that the ZB data is conditional on the structural parameters, the anchors, and the type A data. So that means our random field realizations need to incorporate the type A, the anchors, and be owned by some kind of structural model. Each realization of the target variable field we push into a forward model and we obtain some kind of distribution. So this is an example from ModFlow. This is just a pressure distribution field. When we repeat this process on many realizations, we obtain an ensemble of type B data. We can call this the children that are offspring of the parents, and the parents are that conditioning information, the theta, alpha, and ZA. We infer the PDF of the type B data, and if you're not familiar with nonparametric density, here's a simple animation that should help to evaluate the likelihood of the parent reproducing the type B data. So ZB is our measurement here. The little red curves represent, and the black lines actually represent smooth histograms called kernels placed around the generated data, and we build the entire PDF and evaluate it. So it's constructing this curve, which is a rather high expense, but in the end, the likelihood is still just a single scalar deterministic value. When we obtain the likelihood, we combine it with the prior, and using that mad proportionality, we obtain the posterior. If we repeat this process for multiple samples in the parameter space, we can obtain a full posterior distribution for the parameters. Now, I promise that was rather technical, but I think it's time to see it in action, and I hope this will glue together some of the concepts. So our goal in this simple example that we're going to show in the software is we want to obtain posterior PDFs of geostatistical model parameters and anchor location, transmissivity at anchor location. So our target variable in this case is transmissivity. We have a structural model that's geostatistical, and we have PDFs of the transmissivity at specified locations called anchors. We want a condition on measurements of the pressure head. This is indirectly related to transmissivity in 2D flow problems via the flow equation. And we have some direct measurements of transmissivity. So we have type A and type B data as well. So final notes of the implementation is we will generate the random fields of transmissivity using the package called GStat, developed out of Utrecht. I can't remember Utrecht. Sorry, I'm forgetting the exact location, but we can provide a citation if desired. And then we're going to simulate the pressure head data using ModFlow with our software. So I'm going to ask Carlos to step in here and help me a little bit to provide a short demonstration. Carlos, are you there?
Yes.
Okay.
Yes.
Can you request control of the screen and drive a little bit?
Okay, request control.
Perfect, perfect. Okay, you should have access. So what we're looking at now is the MAD, I guess, plugin. And what we have here is a setup where we have a pre-processing block, which is going to configure all the type A and type B data, the structural model, the anchors, and kind of all the necessary odds and ends of the project so that the software can automatically generate fields, execute the forward model in batch mode and in large quantities. So we start by opening a project here. It's a little bit easier than showing a project built from scratch. The data requirements would also necessitate waiting a long time before we could show results. But as Dan said, before we move on from this screen, there's a forward model and a random field generator that are attached to this MAD software. So our software is a framework that needs to have these kind of controls over these other tools. And the reason we have the attachment be part of the configuration process is so that the models are interchangeable. So if hydrology and ModFlow is not your cup of tea, you can attach your model rather simply without having to change the actual framework. So yes, Carlos is highlighting the configure button. So we start initially by requiring users to supply us a spatial domain. Now, the spatial domain here, Carlos, if you could open a domain up. The spatial domain here is simply because you cannot compare measurements that are outside of where you cannot simulate data outside of where you collect it and compare it to anything. It needs to be compared at the exact same location at the exact same moment in time. Carlos, is it working?
I think Carlos may have just dropped audio, Matt, so you might want to take control.
Okay, I'm going to try to navigate and talk. Sorry if there's some pauses here. So we open a domain, and many of you should be familiar with a lot of the mapping tools that are available. I could turn on a base map, but it kind of slows down the execution of my software right now. So in the interest of expediency, I'll just show we have a map window on the side here where we're going to kind of accumulate all of our spatial information. We then specify our target variables. Now, this is kind of a twofold list. We here classify transmissivity as our target variable, and we also have to say immediately what data we want to condition on. So I'm going to be, as said before, defining transmissivity fields, characterizing them, and I'm going to be using head data for information. After we define our target variable, now we get into the more kind of specifics of MAD. We define the type A and type B data using the measurements tab. So here I have some type A measurements. I can show the legend here briefly. We have blue squares is type A data, pink triangles is type B, and then we'll get to anchors in a minute. So you see as I move through different locations, a different icon highlights in yellow. So I provide the variable value, the location, and the value. And in type B, here I can support transient data. So our distributions actually have time series affiliated at a certain highlighted location. So we can also we support loading of data by text files, so it's not all manual entry for this kind of data. If there's any transformation of the target variable, commonly in hydrology we use log transmissivity or log conductivity. So you can apply a transform to the variable. It'll manage it in the measurements as well. And here I can define a structural model. So here I've defined a geostatistical model that has an exponential covariance, and I've determined some of the variables of this statistical model should be random, and hence an element of theta, the structural parameter vector, or if I want to treat them as deterministic. Of course, any random variable will be assigned a prior distribution, and we'll come to that. But to close out the parameter space, we've done the partition related to structural modeling. Now we move forward to adding anchors. Now anchors are indicated by the black stars in my map. I hope the shape is actually, there we go, zoom to extent there. So the black stars are different anchors. So these are the locations where I'll be getting PDFs of the transmissivity directly. So with all this information, I've completely defined the parameter space and the data space of MAD. At that point, I need to add a prior distribution, which we have this simulation tool that reads in fields from a text file and links them to the random variables previously defined in the project, and proceed to defining the data for my likelihood function. So this is a two-part tab where we have first the locations. Any type B data is eligible for selection. I've selected here 3 points. And then the time series. At each location, I can select any data from within the time series or some kind of compressed representation of this data to keep the dimensionality of the likelihood reduced. So at this location, I can scroll through the 3 different drawdown curves at my different boreholes. Now here, there's also what we're doing is trying to represent these long time series with a fitted polynomial. So we have a tool for fitting a regression onto different segments of the curve. The idea being that you reduce the dimensionality and hence the cost of the calculation by using fewer data points in the likelihood function. But I don't want to get too deeply into that. Now we come to the kind of I guess, maybe the grand finale of the configuration is the fact that we can now completely control random field generation, data simulation, and data management automatically from this tab. It's very nice in terms of inversion modeling. If you've ever done anything before where you did a Monte Carlo process, you know that there's a lot of data generated, and it can be quite cumbersome to maintain all of it. So I'm adding here a time reference because I have transient data, and ModFlow will output something like time 0 without a calendar date. This is the time reference is so that you can link calendar dates to the simulation window. This synchronization evaluation button, please let it run for 1 minute, will evaluate whether the data string, the date string that you loaded as measurement data here in red is coincident with the forward model output. So if the forward model output does not overlap some of these measurements, you will not be able to use them in the likelihood function. So it's nice to be able to verify that this is working beforehand. And We also have parallel processing options and the ability to kind of start and stop. So there's 5,000 samples here from the prior parameter, which is much too many, and normally 3 realizations per sample is far too small, but just to show briefly what we're doing here. Excuse me, sorry, let me quickly change this. You can make this okay. And show you in our data folder, we are creating quite rapidly these X databases which store all the output of the type E data accordingly for the samples that I've selected. So these are quite small, so they generate very rapidly, but often this can be the sizes of several hundred kilobytes, thousands, or even gigabytes. So you see now that the data for the first sample is complete, and it should start to populate the second sample very briefly here. This process is running in parallel on my 2-core machine, and I can interrupt it as needed if I need to manage other things on my computer. So it's very easy to set it to run all night. Sharing information across multiple machines is also very simple. You just exchange folders full of data, and then you can analyze everything concurrently in the post-processing tab. So all the effort to create this big pile of data is to obtain conditional distributions. So without further ado, I'm showing some results that we had to generate previously. You can't really create enough data to get meaningful results in the 10-minute demonstration. So we are simply opening the same project that I generated before. Everything is the same. We have the ability to look at the data that we generated, so we can do these nice summary tabs. For a given sample, this is a value of the structural parameters and anchors. We see that the head drawdown curves, I'm sorry, let me make this much larger so we can read the labels. The black line is the true measurement, and we see that there's 1 standard deviation, the expected value, and 1 standard deviation below the expected value for the head drawdown curves affiliated with this sample, all the different fields that were generated with this. We see that because the black line moves out of the curve, that this might not be a very probable sample for reproducing our field data. So it's nice to have this kind of quick analysis tool, at least to visually check. If I wanted to actually use less of the data than I had started with, I can select a subset or create a subset of the measurements that I saved at this stage, but we'll just move forward here. Computing the likelihood is as simple as it sounds. Once you've generated the data, we want to come in and make maybe perhaps demo 1, a very quick example. Normally you would do all your samples and all your realizations, but this can take a couple minutes, so I'll try to be very brief here. We have to configure a few parameters. These are simply settings of the nonparametric density tools that we have built in. So you have a couple options. You can quickly compute a likelihood. You'll get a notification that it's complete, and it should populate in the tables below. So we have many different variations because often you want to compare different likelihoods in analysis. We have some tools here for convergence. So I'll show this very briefly. When you're trying to evaluate convergence of something that's invested or estimated nonparametrically, you're looking for some kind of stabilization to the values without additional samples being added. So what we have here is the likelihood for a sample is each color on the y-axis, and then the number of realizations used to obtain that likelihood. And you're looking for this kind of very steady horizontal behavior. Often, if you don't have enough realizations, the data can be very sensitive to the number of realizations used, and your likelihood value is not stable and hence not converged, so neither will be your posterior value. These are efficient tools for verifying that your estimates, the probability density functions in MAD are in fact realistic. And finally, we move here now to evaluating posteriors. And this is the whole purpose, is to get to final results. So we can generate graphics here that compare prior and posterior curves. This is a very nice result in my opinion. The field generated here was synthetic, so we knew the results. The actual value for this anchor is around -3, which is about here on the axis. And we see that based on the head information that we conditioned our anchors on, our prior estimate was in red, and the conditioning data actually shifted our posterior to be basically place the mode right on top of the actual value and with a tight variance. So this is the kind of results that we hope to obtain. Nicely, this can be, you can take the maximum value of this for a maximum a posteriori kind of analysis. You can also integrate over the uncertainty, find standard deviations, variance, but having the complete PDF is a very powerful tool because it can be condensed into any of the simple estimators. But with that, very quick and rapid demo. I hope I haven't left off too much, but I'd like to turn the presentation back to Professor Ames to highlight some of our longer term goals and open up for questions.
Okay, thanks, Matt. So let's see, I'm just going to say a couple of things about the architecture, the approach we've taken with this software. I'm pretty excited about it as an example of a fairly complex plug-in software that works with Hydra Desktop and the broader HIS. There are a few things that we want to do as we move forward that will tie in even a little bit closer with HIS, which I'll mention here in a moment. The key cool parts of the architecture are using the key cool part is the extensibility framework that we've adopted from Hydra Desktop, which is called the Managed Extensibility Framework. This is something that is provided by Microsoft in the .NET framework, and what it does is it allows you to easily extend any piece of software with plugins that are added at runtime. And so what you noticed there early on in Matt's demonstration was that the ModFlow model was brought into this statistical analysis environment as an external piece of software. And that was done by writing a driver. As you can see circled here, we have plugins such as Hydra R and MAD that live inside of Map Windows 6 or inside of Hydra Desktop, inside of .spatial on the .NET framework. We followed the same exact approach to allow things like different models and different geostatistical packages and geostatistical simulators to live inside of this broader framework. So this is one cool technology that we're using that is worth making a note of. Just to graphically show you what MEF does, allows you to essentially construct software at runtime by discovering binaries that are then plugged in. The MAD modular architecture is essentially a combination of pre-processing and posterior analysis here on the left, a set of interfaces that define what a geostatistical package should look like, what a conditional simulator should look like, and what a forward simulator should look like. And then we have, so this is the whole MAD piece on the left. On the right-hand side, we have the plugins. So for geostatistical simulation, we've written a plugin for R and GStat. Also for the simulators, we've written plugins using R, and plugins could also be written for MATLAB or other types of software that might provide that simulation capability. And then perhaps most importantly are the plugins that provide different hydrologic models. We're working on, as part of our project and the software release this next month, drivers for both ModFlow and Hydrus. And if there's anybody on the call or listening to this later on YouTube who says, hey, we've got a really cool model that ought to have a driver made for it so that we can do this inverse modeling with it, then please contact us and let us know, and we can work with you and show you how easy it is to make a driver so that it'll work inside the interface. So just to summarize, what we've created under this project so far is a Hydra Desktop plugin version of MAD framework that is launched off of the toolbar in Hydra Desktop, which we didn't show you in this demo. This is tightly integrated. It does not use the web interface at all, but is simply a desktop application that plugs directly into Hydra Desktop. And we've also made a version of it that stands alone. And so this is an approach you can do with your Hydra Desktop plugins, is basically create a thin connector between Hydra Desktop and a button on the toolbar there that launches out this secondary application, which may have the ability to read and write from the Hydra Desktop databases. to show what this looks like now, we have essentially two different applications. On the on the left, the MAD desktop application, and then the MAD and Hydro desktop. As we're moving forward, we're actually working on creating a core MAD computational engine that is just going to be C++ executables that will be cross-platform, with the idea that these can live on the back end of a desktop application or a web application, or even be used in high-performance computing front ends. This is exciting because we did promise in our grant that we would come up with a very a good architecture. We think there's actually even a better architecture to pull things apart. We would encourage people working on similar types of projects with relation to Hydro Desktop to make your core functionality separate, perhaps in terms of separate DLLs in C++ or Python, so that they're a little bit more modular. Our approach moving forward is to take our desktop application. We're actually taking the code from the plugin version and merging it inside the desktop application so that we only have one code base to support, as you can see here in my animation. And this will hopefully make the software a little bit more tractable and supportable down the road. And the CUAHSI logo is there because this is a project that Dr. Yoram, Rubin, and Rick Cooper of CUAHSI have discussed over a couple of years ago as having it be an example software that could receive some sort of support through the CUAHSI Hydro Data Center. And that support is yet exactly to be determined what shape it will take. But at very minimum, we intend to continue to make the software compatible with the CUAHSI software framework and have it available to download and accessible through CUAHSI links. And that's the goals. The reason for that is obvious because we anticipate a large number of our potential users are actually hydrologists with connection to CUAHSI. This desktop application, the Hydro Desktop plugin, is being released on May 1st for testing. We have not built the MAD core yet, which will be the C++ version, and we expect that to happen over the next year or so with the command line executables to run each of the components that Matt showed through a command line to support high-performance computing and even to support a lightweight web-based application just for educational purposes. And to wrap up our presentation today, I'm showing you a screenshot of the URL where this software is being developed. It's at mad.codeplex.com, and that sort of follows the pattern that we've been using with the other CUAHSI Hydro tools, Hydro Desktop and Hydro Server and Hydro Catalog, that have been developed and posted on CodePlex for code management. So you're welcome to go there. We have been doing a heavy push in the last month or so to get a version ready for release that's clean, that's well documented, and has a really good couple of tutorials associated with it that will be available here in an official release come May 1st. And of course on this website you have access to the source code and discussion forums where you can ask questions about the software. In summary, what we've done is created what we think may be one of the first open source extensible frameworks for inverse modeling that's out there. This is intended to be to lower the bar for entry to inverse modeling. Modular implementation is intended to help it be long-term sustainable and meet this NSF goal that we're all hearing a lot about, having to do with sustainable software. By following this modular approach, we hope that other people who are interested in doing inverse modeling with different models will be interested in just playing with this software and working with us and growing it and improving it in a sustainable, long-term way. And ultimately, the relatively, notice my parentheses, relatively user-friendly nature of the software should encourage adoption, we hope, of the inverse modeling technique in general and MAD specifically by both researchers and educators. And we recognize the fact that it really isn't that sort of obvious or transparent how to get started and use a tool like this, but we feel like we've lowered the bar significantly compared to what it may have been previously, and we're certain that there's more that can be done. So with that, that's the end of our presentation. Thank you, all of you that have joined us today, and I'm going to turn the microphone back over to John Pollock at CUAHSI in case there are any questions.
Well, thank you very much, Dan, and thank you, Matt and Carlos, as well. At this point, I definitely would like to open it up for questions, and if you do have a question, please go ahead and type it into the chat box, and then I will read it aloud, and we'll address them as they come in. So if we have any questions, please do type them in the chat, and I see we have one hopefully coming in here. So I actually have a question to start with. How long has this development effort been going on for, Dan?
So we started the MAD project approximately a year and a half ago. And so the MAD interface and all of the software that you just saw demonstrated is about a year and a half old since it was born. However, having said that, Dr. Rubin and his colleagues at UC Berkeley have been developing the technique and prototyping it and using largely the R software package for several years. And this original, I guess there are a couple of important papers that introduced the topic that were 2010. This software is quite new, though. I'm actually looking at our MAD Codeplex homepage to see if I could answer that question better, figuring that about the time we created this was about the time the project started, and that was about a year and a half ago.
Okay.
It looks like, yeah, I see Alva typing and Alan typing. It might be okay just to open the mic. Okay, there, go ahead.
Okay, here we go. From Alan, are there any less computational intensive methods that might be usable, that especially for estimating initial results?
Yeah, thanks, Alan. Appreciate that question. That's a really good question because, as you noticed, we had to do several simplifications for the demonstration today to make it less computationally intense, to even be able to do this demo in an hour. So in the spirit of lowering the bar, I think there are other inverse modeling techniques that could be actually brought in to the framework down the road. And I think there are also some simplifications that could be done to get some initial results right away using MAD. Matt, do you want to take a shot at answering that also?
Sure. There's quite a number. There's a kind of a family of pretty well-established methods, at least in hydrology, that are kind of loosely based on optimization or Bayesian principles. Commonly, you've probably heard of maximum likelihood estimation. This is something that was done, I think, by Kitnidis and Dagan in the early 80s. That's much faster. There are also a variety of methods that don't infer the likelihood function, and that's where we incur the majority of our cost. If you assume to know the shape of the likelihood function, the cost of the process decreases considerably. And there's a bunch of commercially available, and maybe not even commercial, I should be careful using that word in a software conference, softwares like PEST that do parameter estimation that are built into a lot of the other, I guess, forward models around, like Hydrus and Modflow both have these packages attached, except they don't offer quite as much characterization of the uncertainty. They just give an estimate. So there's a little bit of trade-off for the simplification.
Okay, so we have a question from Alva. For one specific target parameter, the user has two observables which can be inversed to get the parameter through two different forwarding models. In this case, is the current system able to address this issue to get a consistent estimate for the target parameter?
That's a really good question. Right now, currently, this would be have to be adopted in a sequential manner. The nice thing about the Bayes law is the posterior from your first inversion, I guess, for the first observable can be used as the prior for the second observable. And then you can link the first model, do the simulation, and then link the second model accordingly. right now that would probably be a rather challenging inversion, but long term the goal is to support that because it's a generic ability of the MAD theory.
Well, it doesn't look like we're having any more questions come in, so again I want to thank, oh actually we have another follow-up from Alba. Is the forward model pure a geostatistical model or is it based on geophysical theory? In the latter case, does the user need a Jacobian matrix?
Let's see, I can tell you that there are two kinds of, sorry Matt, I'll just say one part and then let you answer the second part, but the driver technique that we've done from the architecture point of view supports a geostatistical driver as well as a forward model driver. And so the forward model would be the geophysically relevant model, such as ModFlow, which tries to simulate movement of water through the ground, versus the geostatistical model, which tries to characterize the distribution of some spatial, some sort of spatial feature. Now, Matt, do you want to take a shot at this Jacobian question? I'm not sure the answer to that one.
I think the main clarification I was going to offer here was that the forward model is, I guess in our parlance, what simulates the physics of the problem. And the geostatistical model represents the structure of the target variable. So if you have geophysical data, it can be incorporated in the prior, because maybe you can identify a soil type, and that, I guess, constrains the possible geostatistical parameters of the problem. I'm not sure I quite understand where the Jacobian mixes in. This might be one to open the microphone on, John.
Okay. So Alba, I've unmuted you, so if you want to follow up with that question.
Yeah, Ping is here. Is going to ask the question.
So is it open now?
Yes.
Okay. So I'm asking this Jacobian matrix question because in the forward model based on geophysical theory, and you can get the sensitivity of the output to the input, right? That's how you can do the inverse. So I just wonder, is this the mechanism you are like implementing now, or you have some other mechanism to get the target parameter?
Yeah, it's actually not a sensitivity-based approach, although that is one of the outcomes that I imagine you can calculate with the amount of data generated. There's really no direct inversion in MAD. It's Monte Carlo approach on a large scale for the forward problem, the physics, and then the formulation and the characterization occurs via the Bayesian format. And so the likelihood function is where that kind of transfer of information between the data and the parameters occurs. It's not, no Jacobian involved.
Okay. So then, another question for the observers. So you have this assumption so that we can have this built-in inverse modeling. So what if the observers, they are not follow some kind of PDF, like normal PDF, then does the current system allow the user to field some data to get that sort of normal distribution for the observers?
If you're confident that the observables follow a normal distribution, you can assume a parametric likelihood function and use the data generated to determine the parameters of the normal distribution, the covariance and the mean. But that would, I guess, at some point you'd want to confirm the normality of the data before making an assumption like that.
Okay, so you have you give the user the flexibility, like depending on what decision they make, like in the current system, right?
Yes, there should be. I can actually. Is my screen still showing, John?
Yep.
Oh, okay, good. I can show it very quickly here. You can choose to do a parametric method for likelihood calculation. So right now our typical applications, all the applications that have led to publications with MAD have used nonparametric likelihood calculations. But this is a list that we intend to expand. So right now you could treat your likelihood data as multivariate Gaussian, which is a common assumption for objective functions like in the pilot point method or in the ensemble Kalman filter use multivariate likelihood, or multivariate Gaussian, sorry.
Okay. I'm also interested in the extendable ability of the system. So right now, this math is specific for hydrological system, right? Is my understanding right? So is this be able to extend it to some the other like Earth modeling system? Not just limited to hydrologic system. Like
it is not limited to hydrologic systems, and that, I appreciate you pointing that out because we wanted to make that clear that the framework is more focused on the inversion technique and bringing models into inversion. So any kind of model that can sort of fit with this framework would work, whether it's an Earth system model or an air model or water model. Sure.
Yeah, that would be very nice because in the remote sensing, they have a lot of needs. You know, if you have a different perspective to look at how you use inverse methods, that would be great.
Cool. Thank you, and thanks for giving us some good questions and some good follow-up. There might be others that watch this video later that have similar questions, so hopefully your questions help answer them too.
Thank you.
Yeah, I guess I want to add one comment there real quick. And to reinforce what Dan says, you'll see that none of the tabs here that require configuration actually say anything related to the forward model. The examples we've given are hydrologic because that's my area of study, so it's kind of my comfort zone. But all of these tabs actually only relate to the statistical framework. And the forward model is attached at the beginning to provide some context and to help the tabs adapt to the problem being specified, but they're designed to be able to just supply the statistical framework around the physical problem.
Great. Well, thank you very much, Matt, and thank you, Dan and Carlos as well. And thank you to all of you for attending today's seminar or maybe watching in the future. And I would like to remind everyone that we do not have a cyber seminar scheduled for next week. The next cyber seminar will be in 2 weeks from today at 3 p.m. Eastern, and that will be given by Dr. Alba Couch, who is the director of the CUAHSI Water Data Center and also a professor of computer science at Tufts University. And he'll be talking about the new CUAHSI Water Data Center, so I hope all of you will be able to join us then. And if you, just a reminder, this video will be posted online, and if you would like a notification of when it's posted, please feel free to email me at jpollak@cuahsi.org. And thank you again, everybody. Have a good one.